Hey guys, boundary layer theory is a simple chapter in fluid mechanics, yet an important one. We shall see what is boundary layer and its function and behavior. Now we shall see the concepts in boundary layer theory by answering 5 questions. Let's start with the first one. Shape factor is the ratio of displacement thickness to momentum thickness to energy thickness, displacement to energy thickness, or none of these. So what is the ratio between two, which is called as shape factor? We have three thickness in boundary layer: displacement, momentum, and energy. Here the shape factor is the ratio of displacement thickness to momentum thickness. Now we shall see the definitions of all the terms. First one, boundary layer thickness. What actually is the boundary layer? Here you can see in this diagram. It is defined as the distance from the body surface. So this is the body surface. This is the body surface up to which the velocity reaches 99% of velocity of mainstream. So here you can see the velocity of mainstream or free stream velocity. So this velocity, like 99% of this velocity is reached here. So this distance is termed as boundary layer. This distance is termed as boundary layer and is denoted by delta. So mainstream velocity is denoted by u suffix infinity. Next we shall see the displacement thickness. It is defined as the distance by which the body surface should be shifted in order to compensate for the reduction in mass flow rate. So what actually is the mass flow rate? Kilogram of water per second. So that is the mass flow rate. So to compensate for the reduction in mass flow rate, here you can see the reduction. Actually this is the profile, velocity profile varying in this uh, body surface. So here there is some loss. Here there is some loss, right? This loss is compensated by the displacement thickness. So it is defined as the distance by which the body surface should be shifted in order to compensate for the reduction in mass flow rate on account of boundary layer formation. So this is the boundary layer that we have seen in this diagram itself. Next is the momentum thickness. In the same way, it is defined as the distance from the actual boundary surface such that the momentum flux corresponding to mainstream velocity u infinity through this distance, that is theta, that is nothing but momentum thickness, is equal to the deficiency or loss in momentum due to the boundary layer formation. So there will be three losses. One is displacement, one is the reduction in mass flow rate, so that will be compensated by displacement thickness. Another one is loss in momentum, so that loss in momentum will be compensated by momentum thickness. And next is the energy thickness. Energy thickness means there will be energy flux, energy per second, we can say energy flux corresponding to mainstream velocity. So that deficiency will be compensated by energy thickness. So these three are more important one, and we shall see the relation between what displacement thickness and the velocity profile. So first we shall see this displacement thickness is given by del star equal to integration 0 to del is nothing but boundary layer thickness 1 minus u by u infinity. U is the velocity at that point, and u infinity is the free stream velocity. So this is how we have to see the relation between velocity profile and displacement thickness. And next is the momentum thickness. So theta is equal to integration 0 to del u by u infinity into 1 minus u by u infinity dy. Dy means nothing but the smallest vertical distance. So that's dy value. And del double star, that is energy thickness, is denoted by del star star, or it can be del suffix capital E. We can denote with any term. So that will be given by this equation 0 to infinity 0 to del u by u infinity into 1 minus u square by u infinity square dy. So these are the three major relations in boundary layer theory. By using this relations, we can find the energy thickness, momentum thickness, displacement thickness, momentum thickness, and energy thickness for that velocity profile distribution that is given for us. And there is another point: displacement thickness is always greater than energy thickness, and that will be always greater than momentum thickness. So from this we can get momentum thickness is always lesser and displacement thickness is always greater. So that is why shape factor always greater than 1. What is shape factor? Displacement thickness to momentum thickness. Right, displacement thickness to momentum thickness. We know displacement thickness is always greater than momentum thickness. So that means shape factor for any velocity profile distribution, that will be greater than 1. Shape factor always greater than 1. So these are the major definitions in boundary layer theory. Now we shall move on to next question. Second question is, in general, velocity profile in laminar boundary layer may be taken as. They have mentioned the laminar boundary layer. So what could be the velocity profile in a laminar boundary layer? There are two boundary layers. One is laminar and turbulent. So in case of laminar boundary layer, what could be the velocity profile? So option C, u by u infinity, or u infinity is nothing but free stream velocity. So this ratio will be equal to y by del the whole square. Del, what is del? Boundary layer thickness. Now we shall see for turbulent layer. For turbulent boundary layer, this could be the what velocity profile shape or velocity distribution profile. So that is nothing but seventh power law. Here you can see y by del power 1 by 7. So it can be called as seventh power law. It is a general formula. Not always it will be like that. It can be like this, but not always. In general, we are saying for laminar boundary layer, u by u infinity equal to y by del square. In case of turbulent, it will be seventh power law. And if in case u by infinity is given as y by del power 1 by m, then del star by del, what is del star? Displacement thickness divided by del equal to 1 by 1 plus 1 by m plus 1, and momentum thickness by boundary layer thickness is equal to m by m plus 1 into m plus 2. This can be remembered as a thumb rule, or we can even derive by using the previous formulas regarding momentum thickness, energy thickness, and displacement thickness. But it could be good that if we remember these two relations, we can just substitute the value of m, so that we can find the value of momentum thickness and the value of displacement thickness in terms of boundary layer thickness. Now we shall move on to the next one. Third one is, in a laminar boundary layer over a flat plate, the ratio of stresses tau1 and tau2 at two sections 1 and 2 at distances from leading edge. So what is the leading edge actually? For example, say this as the flat plate. This is called as leading edge and this is called as trailing edge. So they have asked the ratio of shear stresses tau1 and tau2 at sections 1 and 2 at distances from leading edge such that x1 is x2 is equal to 5x1. For example, say this is x1, and what will be x2? X2 will be 1 by 5th of x1. So at this section and at this section 1 and 2. So this is 1 and this is 2. So between uh, for these two sections we have to find the shear stress and we have to get the ratio between them. So how to find that? That is the main concept behind here. We have only one data, that is the distance from the leading edge at those two sections. So by using that distance from the leading edge, we have to find the ratio between the shear stresses of two sections. So here the answer option A, root 5. Now we shall see how it is given or how it is calculated. This will be given on the basis of Blasius results. Here in this table you can clearly see for laminar profile or laminar boundary layer, these are the relations or formulas we have to follow, and in case of turbulent, these are the things we have to follow regarding Blasius results. And when a flow or when a boundary layer or a flow over the flat plate will be called as laminar when the Reynolds number at that section shall be less than 5 lakhs. When Reynolds number is less than 5 lakhs on that section over a flat plate, flow over a flat plate, we can call that as laminar flow. In case Reynolds number ranges from 5 lakhs to 10 power 7, then we can call it as turbulent. And in case Reynolds number is more than 10 power 7, then there exists as another set of formulas that here we are not studying, that will be beyond our scope. So we are restricted only to study the Reynolds number up to 10 power 7. So just we shall study these 6 relations alone. Now we know that Reynolds number is given by rho v d by nu, or we can say v into x by kinematic viscosity. So here actually x is the characteristic dimension. In case of pipe flow, characteristic dimension is diameter of that pipe. So that is why rho v d by nu. We have studied like that. But here the flow is over a flat plate. So that's why here we are writing x. X means the characteristic dimension in this type of flow. X is nothing but the distance from the leading edge. Here you can see the relations like del by x is equal to 5 by root rex. So how the boundary layer will be changing with respect to x? Del is equal to 5x by root rex, and root rex and rex is nothing but vx by gamma. Taking v and gamma as constant, x will be here root x, and here x will be there because this x is coming out here. So 5x by root x. So x can be written as root x into root x. So that's why del is directly proportional to root x. I hope you got the point. So that's why del is directly proportional to root x in case of laminar flow. And it will be different in case of turbulent flow scenario. Here del by x is equal to 0.376 divided by Reynolds number power 1 by 5. So here the variation will be somewhat different when compared to laminar flow. And we shall see how tau is varying with respect to x. Here you can see Cfx is equal to 0.664 divided by root Rex, and Cfx is nothing but coefficient of friction. So that's why tau can be given as half rho u square. U here is free stream velocity. For example, drag force can be given as Cfx into half into rho a u square, or u suffix infinity, free stream velocity. So now we have to get the shear stress. So that's why fd by a. So here a will come. Then how it will be varying? Fd f, or we can say shear stress is directly proportional to cfx, and cfx is inversely proportional to root rex, and root rex contains x. So that's why tau is inversely proportional to root x. I hope you got the point. So this is how del varies with x, and this is how tau varies with x. Del is directly proportional to root x, and tau is inversely proportional to root x. And just substitute this relation with the given data, like tau 1 by tau 2 is equal to what? Root of x2 by x1. So just substitute, you can get the answer as root 5. So this is how we have to find the thing. Here we have studied about the boundary layer thickness with respect to laminar flow, how to find that with how it is varying with the Reynolds number, and next we have studied about the CFX, or we can directly say shear stress, that is shear stress is equal to CFX, that coefficient into half into rho u squared. And next is the drag force or drag coefficient. So that drag coefficient is given by 1.328 divided by root RL. So here L is given. Why? Because we are taking the total length of the flow, not at somewhere like not at some section X. So drag coefficient will be taken for whole length. Then what is the Reynolds number? V into L by nu. V into L by nu. Nu here is kinematic viscosity. And similarly, we can go through the formulas regarding turbulent flow. Del by x is equal to 0.37x 376 by Reynolds number power 1 by 5. And similarly, CFX and CD. We need to know these six relations, and we can expect some questions like this in many examinations. Now we shall move on to fourth question. This question deals with laminar sublayer. Here they have given us laminar sublayer appears only when the plate. So how the plate should be so that laminar sublayer will appear. Whether the plate should be rough, or it can be smooth or rough irrespective of that, or it should be very smooth, or plate should have a roughness index above 1. How the plate should be? The plate should be very smooth in order to get laminar sublayer. Here in this diagram you can see actually this K is nothing but the height of roughness. This is uh, first diagram refers to the flat smooth plate. Second diagram refers to rough flat plate. Rough means there are many roughness you can get here. Many roughnesses are there, rough surface. So that's why the roughness length is very large. So the K value is very large when compared to laminar sublayer thickness. So that means in a rough plate, laminar sublayer do not exist, because you can see this dotted line. Above this dotted line also there is some roughness. Here lies the laminar sublayer. So what that indirectly means, laminar sublayer is not appearing in a rough flat plate. In case of smooth flat plate, this is the smooth flat plate. Roughness is very smaller than a rough plate. Then laminar sublayer will be appearing. So this is the concept. And here also you can see this is the flat plate. Consider this as a smooth flat plate, and this is the laminar region, this is transition, and this is what, turbulent region. And in the turbulent region only we are getting the laminar sublayer portion. This clearly mentioned here. In the turbulent region only we are getting the laminar sublayer. So that means laminar sublayer concept can be studied on a turbulent flow. So we shall study in detail about laminar sublayer when we deal with the turbulent flow chapter in later. Now we shall continue with the basic concept behind it. Laminar sublayer velocity over the laminar sublayer is considered to be parabolic, normal parabolic velocity distribution. But because of the thickness of the laminar sublayer is very less or very small, we can assume it as a linear profile for easier calculations, nothing else. And the laminar sublayer thickness is given by this relation, del dash is equal to 11.6 gamma by V star. Here gamma is nothing but kinematic viscosity, and V suffix star is the shear velocity, and that will be given by root of tau naught by rho. So tau naught shear stress, rho is the density. So these are some basic concepts in laminar sublayer. We will see more in detail in when we deal with turbulent flow. Turbulent flow chapter is a separate one. In that one only we shall deal with the shear velocity like that. And next important equation is the von Karman integral momentum equation, d theta by dx. What is theta? Momentum thickness. D theta by dx is equal to tau naught by rho u square. Here x is nothing but the distance from the leading edge. Then what is dx? The smallest distance from the leading edge, we can say. So d theta by dx is equal to tau naught by rho u naught u infinity square. So these are some basic concepts behind laminar sublayer. Now we shall move on to the next one. Which of the following are correct regarding boundary layer separation at y is equal to 0? Option A, at point of separation, velocity gradient is 0. If velocity gradient, that is du by dy, is greater than 0, then flow will not separate. If it is less than 0, flow has separated. That means flow has separated. Pressure will be maximum at x. So this is a point denoting. So what are the correct options regarding boundary layer separation? At point of separation, what is the velocity gradient? When what is the velocity gradient when will not separate? And similarly, flow has separated. So here option A, B, C, first three options are correct. But last one, pressure will be maximum at X is not correct. Why? Because pressure will be minimum at this point, not maximum. So pressure will be maximum at X is wrong. First three points are correct. Now we shall see one by one the points regarding flow separation. This boundary layer separation or separation of flow can be seen in these hydraulic machines like diffusers, pumps, fans, turbine blades, aerofoils, like that. In these hydraulic machines, we can expect separation of flow. So how to control that? We have to control by using some four methods like streamlining the body. So what actually is the streamlining the body? By use of suitably shaped bodies, point of transition of boundary layer, like this is the point of transition as we have seen. Like for the example, this is the laminar flow and this is the transition and this is the turbulent. So the point of transition of boundary layer from laminar to turbulent can be moved downstream, which can which can result in the reduction of skin friction. So thereby we can streamline the body. So again repeating, so by use of the suitably shaped bodies, the point of transition of boundary layer from laminar to turbulent can be moved downstream, which may result in reduction of skin friction. So therefore, henceforth, we can streamlining the body. This is one method. And next is the boundary layer to move with the stream. So boundary layer, if possible, to eliminate the formation of boundary layer by causing the solid boundary layer to move along with the flowing fluid. So that is one method of controlling flow separation. And next, third one is accelerating the fluid in boundary layer. So how it can be done? By injecting the fluid over that boundary layer, we can accelerate the fluid so that we can control the flow separation. And next is the suction of fluid from boundary layer. So when suction of fluid, there will be excess, like there will be turbulent wave happening. So that we can, so in order to reduce that, we can use the suction of fluid from the boundary layer method. Here in this diagram, you can clearly see what happens. Here the velocity gradient is greater than 0 and the pressure is here. Pressure point is here and pressure is going on reducing, and here comes a minimum point. Here comes a minimum point, and that is this point only. And after that, velocity gradient is equal to 0. That means it is at the verge of separation. At the verge of separation. And after some time, velocity gradient becomes less than 0. So then that means the flow has separated. The flow has separated. When the velocity gradient is less than 0, that means pressure gradient is greater than 0. It is like inversely proportional. Here you can clearly see. Here the separation happens, turbulency happening here, and turbulent wake will be happening. So what is the turbulent wake denoting? The large turbulent eddies formed downstream of the point of separation. So downstream of the point of separation is the turbulent wake. We can say bluff body in the flow. So these are the main points to be noted regarding boundary layer separation. So we have studied about the boundary layer concept. What are the thickness like displacement, momentum, and energy thickness, and we moved on to laminar sublayer flow separation like that. So we covered some important concepts in boundary layer theory, a simple chapter yet an important one. Thank you for watching. Also see this suggested video and please share the video to your friends, and don't forget to subscribe the channel now. Thank you so much.